Hi, and welcome to Talking Tech. I'm your host, Alejandro, and today we have a very special guest, and we're going to be talking about Intel security when it comes to the Lunar Lake architecture. With us to talk about this is Nivedita. Hi, Nivedita.
Hey, Alex.
How are you doing today?
Doing great.
Well, so we are very excited to be here to be with you, and this is a subject actually that we're touching for the first time compared to our previous Talking Tech. So you're going to be our lead expert in this, and we can't wait to talk about it.
I'm excited. Yeah.
For Lunar Lake, there's a lot of new features coming into Lunar Lake. Can you give us a quick overview of what those are?
I think from a security perspective, there's a few things happening in Lunar Lake. So when we started off Lunar Lake design, our focus was on, we already have like different security engines focusing on the silicon security, the root of trust on our actual silicon and an engine that provides digital rights management, the graphics security controller. But as we moved into Lunar Lake, we saw the need for creating a new security engine for our partners to be able to develop their usages and run it securely on the SoC. So we have introduced a new hardware called the Intel Partner Security Engine on Lunar Lake. The other new thing that we're going to be talking about that was introduced back in Gen 12 is the virtualization redirect protection. So this technology provides runtime application protection for the virtualization-based environment, which is becoming even more relevant now, which is why we want to talk about it now. It's getting enabled in Windows 24 in time for our Lunar Lake platforms to launch. But as we were working through these things and getting ready to launch Lunar Lake, AI hit us. So definitely there are things that are happening in Lunar Lake in the context of NPU as well as the overall system security that are relevant to protect AI, model AI user data.
So there's a lot of cool new features, and like you said, also AI in there, something that you had to think about completely new that we'll touch in a bit, but it's pretty interesting. So let's talk about a little bit what you mentioned first, the Intel Partners Security Engine. Tell us a little bit more. Is it new? How does it work? And the different kind of features that it has.
Yeah. So the Intel Partners Security Engine, so from a security engine and a hardware perspective, Intel has had like a long history in the hardware that we develop and how securely we design, validate, and maintain our hardware. So it's an instantiation of our leading edge security engine hardware, but it's a dedicated instance because it has like specific functions and usages that we want to keep isolated from the rest of our hardware and including the rest of our security engines. So the primary purpose of the partner security engine, as I said, is the partner usages, this could be an operating system vendor, this could be an OEM who want to develop usages, and they will leverage the hardware provided security services like cryptography, storing specific information that's related to security usages that they would like to execute. One example is, Microsoft Pluton is a usage that will run on the Intel Partner Security Engine.
No, that is great. And we were talking earlier before we started the interview about, I was asking you like if it's physically separated to provide more security to it. And you were saying that it is separated, but there's also other stuff that are also physically separated.
Yeah. So the Partner Security Engine, both from an IP and SoC perspective, we have consciously ensured isolation and security by design principles, right? So first, from an IP perspective, it is going to provide like security services, as I said, like cryptography. These are kind of things that our security engine, the Intel Silicon Security Engine, which is our security root of trust in the SoC, already does. But we still create a dedicated instance of the crypto IP, which we call as the offload crypto subsystem. It is a FIPS certified IP block that there's a dedicated instance of it for the partner security engine to provide those crypto services directly to the third-party usages. There's other aspects of isolation on the IP itself, like the fuse block and fuse controller. For the IP is on the IP. It does not have access to the SoC fuses. But what makes this very competitive and very compelling from a security perspective for our partners is the SoC isolation principle. At the end of the day, from an SoC perspective, there is one fabric, There's multiple layers, it's a hierarchy, but all IP blocks are sitting on this fabric. So when the IP goes to access things like memory or storage or other resources, all of them send their accesses through the same fabric. So one may ask the question of, is this really isolated if everything is sitting at the same level on the fabric, right? So if you were to picturize this, there's the partner security engine, the converged security and manageability engine, and the Intel Silicon security engine, all at the same level on a fabric in our PCD die. But our SoC security aspects ensure that memory accesses from the partner security engine are only sent to a memory region that's accessible to that engine. It cannot, for instance, access the memory available to the host. It cannot access memory that's available to the Intel Silicon security engine. And it's also vice versa. If I'm defining and putting in a partner security usage, I don't want the Intel Silicon security engine to be snooping in on my data and my secrets that I have in my memory, right? So this is a built-in security principle. It's called security attributes of initiator. That's already in our SoC and fabric, and this is what we use to create that isolation that's required for Intel Partner Security Engine. And I gave the example of memory, Alex. This also expands to other things like I/O and storage.
So for that fabric, so there's like is it good to say, like an analogy, like there's like a traffic police cop telling like, okay, you can get onto the fabric. I know you said that the addresses are reserved and you cannot touch them for the memory, but it will be the same for the fabric. Like, okay, right now the partner security engine is going to talk, everybody kind of get off, and he just has pretty much the highway to itself.
In terms of how traffic is routed on the fabric, that's not exactly controlled. Through this security mechanism that I spoke about, there is arbitration that happens on the bus and things like that. But the security changes are focused on, there is a traffic police, but the traffic police is more in terms of looking at, can I see your ID? Are you permitted to be on this bus? Are you permitted to get to this endpoint? Versus, I think you should actually be redirected to that place.
Okay, that makes sense. Thank you. Another curiosity is the fuse box. My knowledge of the fuse box is just like a regular fuse when it comes to CPUs that we can actually go and enable, disable. So does that mean that the partners are going to have that accessibility? Like they're going to be able to access that? Do they access directly? Do they access through us? Just like we do for chipsets, kind of?
Yeah, that's a great question, Alex, because that's a concern for, when you look at the ecosystem, when partners are developing special usages and they are integrated into the SoC, there's always concerns from the rest of the ecosystem on what else are they having access to? So I did speak about access and isolation, but fuse is an important part of it. For a security engine, fuses are extremely critical. There are important decisions that are made, at the time of manufacturing and factory that are in the fuses. There's also, security critical data that's stored in the fuses for security engine. So it's very important that these fuses are not, shared with other blocks on the SoC. And likewise, we wouldn't want our CPU fuses and our own silicon security engine fuses accessible to the partner, software or firmware, which is why the fuse block or fuse macro, as we call it, in the integration world, is dedicated to this engine, and it is not accessible to other engines. And the access that it initiates is through its own fuse controller. Traditionally, IPs would have used a fuse controller that's in the SoC.
Can you give us a little example how a partner will use the partner security engine?
So, one great example of a partner usage for partner security engine, as I said earlier, is the Microsoft Pluton. So Microsoft Pluton is a Windows client-specific set of usages that's designed to make your Windows experience platform more secure. So there's a lot of usages that come behind it that Microsoft has been talking about and they'll continue to talk about. So Intel Partner Security Engine on Lunar Lake is able to run Microsoft Pluton usages directly on the SoC using the principles that I spoke about.
That's great. All right, now let's change a little bit of gears, because now we have moved, the architecture has changed overall when it comes to processors, and we have moved from monolithic to multi-tile dies. And we started that with Meteor Lake. There's some new changes in there that I think we should cover when it comes to security, because that is something completely new when it comes to security, because it also creates some new vectors of attack for when it comes to security?
Prior to Meteor Lake, all of our security services were kind of converged into this, which is why it's called Converge, the Converged Security and Manageability Engine. So from a security perspective, if you look, when we design an SOC, the key things we look at is, system management and flows, then security services that are required for the silicon, and then the digital rights management services that we kicked off like a few years ago with, Clarity and Widevine and other such usages. As I said, prior to Meteor Lake, all of this was part of the CSME engine. There is a value in kind of separating these usages into separate engines by themselves, right? So the Converged Security and Manageability engine, it continues to remain. It focuses on system usages like, the platform trust technology, which is Intel's firmware TPM solution. And it also enables something called as active management technology. And the SOC, the silicon root of trust is kind of now focused in one engine that's called the Intel Silicon Security Engine. So this is one engine inside of the SOC that's providing all the security services that's required for the silicon and the IPs. In a sense, you can say it attests to what is in the silicon. It authenticates all the firmware that's running in different IP blocks within the silicon. And then the third piece, which is the DRM part, is moved to what is called as a graphics security controller. And graphics security controller, because of the kind of services it provides, is also residing on the graphics processing unit.
Well, that's great. So those are present in Meteor Lake and also on Lunar Lake.
Right.
And is there another one on Lunar Lake that we have introduced?
Yes. So in addition to this, when we go into Lunar Lake, as I said, now we have our usages spread out into 3 different engines, and the system services, the silicon security services, and the DRM services is what we were focusing on. But working closely with our partners, which is the OS vendors as well as OEMs, we realized that they also have the need to go and execute different security usages, but they want to do it securely on the SOC, being integrated as part of the SOC. So the partner security engine was introduced. In a sense, it's like a playground where they can run their differentiation and security solutions, but within the bounds of whatever is the boundary of that playground.
No, that's great. So they have a little sandbox to play and just make sure that everything else still runs correctly.
Yep.
All right, let's talk a little bit about virtualization and all the kind of the security threads and how also what you guys have done here to make it more secure.
Yeah. Virtualization is an extremely important topic. So before we jump into it, there may be folks wondering, what's it got to do? Well, we're talking about security, right? So what's going on here? So client ecosystem is kind of migrating to what we call as virtualization-based security. The reason for the ecosystem to move in this direction is to build a secure foundation. So is our hardware capable of being virtualized? The answer is yes. But do we also meet the power and performance needs of a client PC while allowing it to be virtualized? Because that's going to be the default state, right? A lot of the investment that we do is in virtualization technologies that we've built over time, like Intel virtualization technology, Intel VTD, and we continue to build on that. But it's also focused on where do we stand in terms of performance and power KPIs, and where do we need to go fine-tune our hardware in order to meet the needs of the ecosystem, and the PC power and performance numbers. In addition to that, the other thing we look at is, if this is the baseline, are there additional security threats that we need to go address, and how do we raise the bar in terms of security even within a virtualization-based environment?
So with that type of environment, there was also a couple of things that you guys have done differently in there to make sure that there's different types of attacks. I think we're talking about like an alias attack or spook memory attack.
VMAP attack.
Yeah, VMAP attack. Yeah. So can you tell us a little bit more about that and how we're securing that? Well, actually, I think both of them with one type of feature.
Yeah. So we introduced in Gen 12 a new technology. It's called virtualization redirect protection. So a little bit background, when you start having virtualization-based environment, it's, already in a computer, if you understand the basics, every address access to memory is not going as a direct physical address. There is some address translation that happens when you actually initiate the access from a program or something, right? So in a virtualization-based environment, the number of translations that you do before you actually get to the physical page in memory is I will say, one step more. And traditional virtualization-based systems, there is this slim component in the OS which is trusted. It's called the hypervisor. And the hypervisor uses this Intel extended page table concept where it does one level of translation. Okay, so the translation to the actual physical memory is kind of controlled by the hypervisor. So it ensures that the address that it was requested is going to the precise location in memory, and it's not kind of snooping into incorrect locations in the memory. But there is another translation that has happened by the time the hypervisor got the address. So that's called a guessed translation. And what virtualization redirect protection does is kind of extends the protection that we have today with extended page tables to also cover guessed translations. We call it as end-to-end page walk protections, because I have walked through multiple page tables by the time I reach my physical memory. So how do I ensure that all of that is protected and not just one level of translation? So that's kind of what the technology does. What happens if we don't have this? We largely classify this as kernel page table attacks, right? Probably take a step back and explain what that means. So if you're an attacker, you're interested in attacking the device, and one of the attractive areas is kernel pages. So kernel is where the operating system keeps its sensitive, important functions and things like that. So going and accessing those pages, modifying them. So these are things that an attacker is constantly looking to exploit. One such attack is the remap attack, where the access that initiated from the kernel is redirected to an incorrect physical page in the memory. And how that happens is precisely like how I explained. The guessed translation is kind of mucked with, and the hypervisor does not realize that the guessed translation was modified, and it ends up directing it to a different physical page than it should have. The second type of attack is the alias attack, where there is a user mode program that pretends to be a kernel, and its accesses are kind of redirected through the kernel page translations to a page that only the kernel should have access to, right? So these are two important attacks in this overall, what we call as the kernel page exploits. And VTRP, or virtualization redirect protection, precisely addresses them. We have a few hardware changes that went into our CPU to go kind of as I said, that end-to-end page walk protection. One of those is important, which we call as the HLAD page table structure, which is what replaces the existing page table structure to ensure that this end-to-end protection is provided.
No, that's pretty interesting. I mean, I learned a lot of this. Is kind of my second time listening, and it's great because I didn't know. And thank you for explaining, because now
Absolutely.
I understand more of the different types of attacks and how it is going into. So the first attack is kind of intercepting the hypervisor before, like the hypervisor doesn't know really the address that it's going to get, and the attack is intercepting that and using that.
Right.
And the other one is just a spoofing, like, hey, I am the kernel.
All of this still goes through the hypervisor, right?
Okay.
So all of these accesses go through the hypervisor. In both the cases, the hypervisor is completely oblivious to the fact that in the first case, it was basically redirected through a different guessed translation. And in the second case, it originated from a completely different address, but You
come there. Well, I'm glad. I'm glad that it's being secure.
Yep.
Okay, so the third thing that you were talking about is AI and how it's secure. And it's a very interesting topic because in the presentations that you've done, that you did at Intel, the technology tour, you're talking about how we have to protect different things. So let's start from the top. How is the security from a cloud perspective into an actual PC or AI PC?
Yeah, this is one of my favorite topics. I think when we started looking at AI and AI PC, one of the challenges we had in the PC ecosystem, working along with our partners, is trying to understand the threats that could happen for an AI PC. There's a lot of publications and research done on AI in the cloud. There's also technologies and solutions available. but we had to do the due diligence of understanding how this actually executes on a PC, and are we fully covered, in terms of just looking at certain threats, or are there going to be additional things, right? So again, focusing on deployment and actual AI inference and execution on the PC, what we understood was there are additional attack surfaces on the PC when you execute an AI model as compared to the cloud, right? So this put us in an exercise of, let's first understand the flow. What does it mean to go execute an AI model on a PC? In a simple sense, it's an application. Today I have a PC, I execute a ton of applications on it. The applications are signed, they are verified by Windows. If I'm running in a virtualization-based environment, there's some, lot of checks and balances that are happening. But when it's an AI application, it comes with a high-value asset, which is a model. It starts with, if it's a high-value asset, the ISV who's deploying the application is no more just signing it. They're going to want to also encrypt the model, right? Again, this is for ISVs who are concerned about model theft that happens at the time of deployment because it comes over the network. So the first change that we see is, as a user, when I download an application and I just instantly install it and I start executing it, I'm going to now see that I downloaded an application and I have to decrypt a model package inside it before I can start installing it, right? Decryption is, it's a time-consuming, power-consuming process, and addressing that for large components like models is very important. So having the right crypto that provides the best performance. You cannot afford to degrade the performance that we are promising for the AI PC, and also ensures that the power that's consumed is not too high is very critical. The second part is what happens after it gets decrypted. It actually gets compiled before it is sent for inference, right? So now we can just compile it using tools like OpenVINO, etc., that Intel provide, and you can just send it over to whether it's the CPU or the GPU or the NPU, and it starts running inference. But what happens the next time you double click and reopen the same application? It's going to get compiled again, right? So one of the optimizations that was done for the sake of performance, compilation is like a couple of seconds for a big model, was to cache the compiled model, in a sense, and you store it on the disk. So the next time you want to reopen the same application, the model that is cached, which is in a compiled format, can quickly be dumped onto the accelerator where you want to actually execute it. But with this,
you have to encrypt it.
Now I have to encrypt it. Right? So now I perform the task of encryption. I can kind of do that in parallel to actually trying to execute the model. But the next time I open it, I have to decrypt it again. So here again, crypto performance and power savings is going to be extremely important, right? And then we go to the third step, which is the actual inference and execution, where the model is in the cache, it's in the memory, it's shared between the CPU and the two different accelerators that we have in our SoC. And depending on the SoC architecture, it's going to vary on where we are caching, the different model weights and things like that. So then we think about how do we protect the model while it is in use, right? And so far, I only spoke to you about the model protection. There's also the aspect of user protection. So this, in a nutshell, is kind of how we approach the problem of protecting AI on a PC.
That is amazing, because you're completely right. It never occurred to me that the model is a very valuable asset. And of course, the developers want to protect that, and that's why it has to come encrypted. And then it's interesting because I didn't know they had to compile it, and that's going to take time. So I guess you were saying that it's faster or more efficient to just encrypt it, store it, and then decrypt it than it's just to compile it every time that you got to run it.
Yeah, that's actually true. So we are definitely investing in how do we make this even more efficient? How do we make it more performant? How do we ensure the power is even lesser? Even in a situation where we have to do like multiple decrypts of different models in parallel.
So we were talking about how we secure AI, but also there's this thing of how AI can help us to secure things or help us on security. Any examples or anything you can help us with?
Yeah, I'm glad you asked, because using AI for security has been around for a while, but what does this mean for a PC, right? One of the amazing things that we did as part of Meteor Lake, and we also continue to do it for Lunar Lake, is our engagement with security ISVs. So these are security usages that today run on the cloud, and they provide services like detecting, email scams and phishing attacks. They detect fileless malware that is on your system, malware scans, antivirus, and things like that. So these are models that run today on the cloud. There's a cost that's associated with it. There's also a performance aspect. But when we had to bring some of those models down to the PC, there was a big question about, is there enough compute? Is there enough memory bandwidth? And are we going to be able to do this, right? And the Intel, teams, they did an amazing job of partnering with key ISVs, and we were able to kind of optimize their models. And as we go through Lunar Lake into our future platforms, we see more and more such usages shifting towards the PC. So we're able to provide localized security with the help of AI algorithms.
And that's, like you said, it's constantly running. So if it runs in the NPU,
yes,
and which is optimized for power and efficiency, then it's a lot of good savings there.
Right, and there's also like existing technologies like threat detection technology that's offloaded to the GPU accelerator, for I think a couple of generations now, where it runs anti-malware scans that without impacting the overall performance and bandwidth of the system.
It is very, very interesting. It is definitely completely new, and this is great. I learned a lot of everything because this is, like I said, completely new for me. And I'd like to thank you. Thank you so much. Appreciate it.
Thank you, Alex.
Thank you
For your time.